Here are a few questions from the paper Statistical Mechanics. See the first question, what is meant by Brownian motion? In 1827, an English botanist, Brown, discovered this concept. He observed the movement of the pollen with the help of a microscope. The phenomenon was most clear in the case of colloidal solutions. The suspended particles were observed moving to and fro, rising and shrinking rapidly and continuously in a random way. The irregular motion of particles is called Brownian motion. Einstein gave an explanation of the Brownian motion on the basis of kinetic theory. According to him, a particle always experiences an unbalanced force and is continuously driven about in random directions. What is meant by degrees of freedom? The degrees of freedom of a dynamical system are the number of independent motions that the system or particle can perform. The molecules of the monatomic gases helium, argon, and neon consist of a single atom and have only translatory motion. Therefore, their degrees of freedom are 3. The molecule of a diatomic gas like H2, N2, and O2 consists of two atoms connected to each other by a rigid bond like dumbbell. Such molecules can have 5 degrees of freedom. 6 degrees of freedom are available to polyatomic molecules. What is meant by mean free path? The mean free path is the average distance traveled by a molecule between two successive collisions with other molecules. If the total distance traveled after n collisions is s, then the mean free path lambda equal to s divided by n. A formula is available for mean free path, that is lambda equal to 1 divided by root 2 into pi d square n. From this we may interpret that the mean free path is inversely proportional to the number of molecules per unit volume. That is our density. What's the effect of pressure on the mean free path? Lambda equal to kT divided by root 2 into pi d square p is a relation connecting mean free path, temperature, and pressure. If you increase the temperature, the value of lambda increases. If the pressure is increased, the lambda decreases. State the law of equilibration of energy. The total energy of a dynamic system in thermal equilibrium is distributed equally among its various degrees of freedom. The energy associated per molecule per degrees of freedom is 1 by 2 kT. Here K is our Boltzmann's constant. What is phase space? The position of a particle is determined by the coordinates x, y, and z. But these coordinates do not tell anything about the motion of the molecule. Now imagine a three-dimensional space in which the coordinates are the momentum projections px, py, and pz. This space is known as momentum space. A point present in momentum space determines the state of motion of the molecule, but nothing about its position. The combined position and momentum six-dimensional space for a single particle is called phase space, and particularly the mu space. The volume of the phase space is h cube. On the basis of principle of uncertainty, delta x into delta px is h, delta y into delta py is h, delta z into delta pz is also h. So that v equal to h cube. Macro state describes the number of ways in which the given identical non-interacting particles are distributed in different cells. Whereas the microstate tells us which particle is in which compartment. For the given number of n particles, there are n plus 1 microstates. For the given n particles, the possible microstates are 2 power n. For the given number of n particles, there are n plus 1 macrostates. For the given n particles, the possible microstates are 2 power n. What's an ensemble? A collection of large number of particles is known as a system. Similarly, a collection of a large number of macroscopically identical systems that are essentially independent means non-interacting, is known as an ensemble. The widely used ensembles are microcanonical ensemble, canonical ensemble, and grand canonical ensemble. Microcanonical ensemble. It is a collection of a large number of essentially independent systems having the same energy E, volume V, and the number of particles N. The individual elements of microcanonical ensemble are separated by rigid, impermeable, and well insulated walls such that the values of E, V, and N for a particular system are not affected by the presence of other elements of the ensemble. These are all insulated. One is insulated from other. In a microcanonical ensemble, we won't expect the transfer of energy and particles. Canonical ensemble. Canonical ensemble is a collection of a large number of essentially independent systems having same temperature, volume, and the number of particles. The equality of temperature of all systems can be achieved by putting each of them in thermal contact with a large reservoir maintained at a constant temperature T, or bringing all systems in thermal contact with each other. Grand canonical ensemble. Grand canonical ensemble is a collection of large number of essentially independent systems having same temperature T, volume V, and same chemical potential mu. In this ensemble, all the systems are separated by rigid, permeable, and conducting walls. What is density of states in phase space? An ensemble is a collection of a large number of macroscopically identical but essentially independent systems. A point in phase space can represent the instantaneous state of each system. A collection of points in phase space can represent the state of the ensemble. The density of these points is known as the density of states in phase space. Liouville's theorem. The rate of change of phase points in phase space is 0. That is d rho by dt equal to 0. The second part states that there occurs conservation of extension in phase space. D by dt of del V equal to 0. Define thermodynamical probability. The number of microstates corresponding to the given macrostate is called the thermodynamical probability. Thermodynamical probability is given by the general formula W equal to capital N factorial divided by Nn factorial, N2 factorial, dot Nk factorial. Suppose 4 particles are given, N equal to 4. These 2 particles are allotted in 2 compartments. Suppose a macrostate is 2, 2. The possible microstates corresponding to the macrostate is W equal to 4 factorial divided by N1 factorial, that is 2 factorial, N2 factorial, 2 factorial is equal to 1 into 2 into 3 into 4 divided by 1 into 2 into 1 into 2. that is equal to 6. For the given macro state 2 comma 2, the possible microstates are 6. Define equally probable events. When the probabilities of the occurrence of two or more events are the same, then these events are said to be equally probable. For example, when a coin is tossed, the probability of getting a tail and a head is the same. What is Stilling's approximation? Log n factorial is equal to n log n minus n. Is Stilling's approximation. State Boltzmann canonical distribution law. According to Boltzmann canonical distribution law, if a system at temperature T is in thermal equilibrium with a heat reservoir, then the probability of the system existing in any particular microstate of energy E suffix r is proportional to e power minus E suffix r divided by kb into T. P is proportional to e power minus E suffix r divided by kb into T. Here kb is our Boltzmann constant. What are bosons and fermions? Particles obeying Bose-Einstein statistics are called bosons. Bosons have zero spin or integral spin. So, for example, meson, photon are coming under this category. Particles obeying Fermi-Dirac statistics are called fermions. Fermions have a half integral spin. Electron, proton are coming under the category of fermions. Maxwell Boltzmann distribution law. It gives us the most probable distribution of molecules among the various energy states. From the above equation, that is Ni equal to Gi divided by e power alpha plus beta Ei, it is clear that for a higher energy state, the value of Ni is less. Here beta equal to 1 by kT. Partition function. The partition function is the way in which the energy of a system is partitioned among the molecules that make up the system. The value of the partition function increases with the temperature. When the temperature is raised, more molecules will be present at the highest energy levels and fewer molecules at the lowest energy levels. The partition function Q equal to summation or I equal to 0 to infinity Gi e power minus beta into Ei. We know that beta equal to 1 by kT. Therefore, summation over I equal to 0 to infinity Gi e power minus Ei by kT. Bose-Einstein distribution. According to Maxwell Boltzmann statistics, particles have been distinguished from one another. It means that particles interchange their positions and energy states, and a new complexion would arise. According to Bose-Einstein statistics, the particles are considered to be indistinguishable. On interchanging the two particles between two energy states, a new complexion or microstate will not arise. Here Ni equal to Gi divided by e power alpha plus beta A minus 1. Bose-Einstein condensation. We know that Ni equal to Gi divided by e power alpha plus beta A minus 1. The presence of minus 1 in the denominator increases the value of Ni to be greater for Bose-Einstein gas than for the classical Maxwell-Boltzmann gas. It implies that the effect of Bose-Einstein statistics increases the number of particles at lower energy levels. Therefore, Bose-Einstein statistics forces the particles to condense in lower energy levels. Fermi-Dirac distribution. In the Fermi-Dirac distribution, Ni equal to Gi divided by e power alpha plus beta A plus 1. Fermi energy is often defined as the highest occupied energy level of a material at absolute zero temperature. Black body and Kirchhoff's law. A perfect black body is one that completely absorbs all radiations incident on it, irrespective of the wavelength. According to Kirchhoff's law, the ratio of the emissive power to the absorptive power for radiation of a given wavelength is the same for all bodies at the same temperature and is equal to the emissive power of a perfect black body at that temperature. Stefan's Boltzmann law. According to Stefan's Boltzmann law, the radiant energy per second per unit area by a black body at absolute temperature T surrounded by an enclosure at temperature T0 is given by E equal to sigma into T power 4 minus T0 power 4. Wien's displacement law. The product of wavelength corresponding to maximum energy, that is lambda m, and temperature T is a constant. Lambda m into T equal to constant. This is called Wien's displacement law. Planck's radiation formula. According to Max Planck, the radiation from the black body is not continuous, but in the form of small packets called quanta or photon. The energy of each photon is h nu. The energy distribution in the thermal spectrum is E lambda equal to 8 pi hc divided by lambda power 5 into E power h nu by kT minus 1. We know that C equal to nu lambda, the velocity of light equal to frequency into wavelength, therefore nu equal to C by lambda. The above equation is modified as 8 pi hc divided by lambda power 5 into E power hc by lambda kT minus 1. Peculiar properties of helium 1 and 2. Helium gas liquefies at a pressure of 1 atmosphere and 4.2 Kelvin. When the temperature falls from 4.2 Kelvin to 2.1 Kelvin, the boiling stops and the liquid becomes quick. This shows that below 2.19 Kelvin, a new liquid phase of helium is formed. This is called liquid helium 2. The temperature 2.19 K is called the lambda point. The liquid helium above the lambda point is called liquid helium 1. The transition from liquid helium 1 to liquid helium 2 is marked by sudden discontinuities in certain properties such as density, viscosity, specific heat, and thermal conductivity. It was observed that when the temperature of liquid helium falls from 4.2 Kelvin to 2.1 Kelvin, the density increases but further drops in temperature, the density suddenly begins to decrease. Similarly, the specific heat of liquid helium first decreases and then increases up to 2.19 Kelvin, and at this temperature there is a sudden and abnormal increase in the specific heat. The viscosity of helium 1 decreases with a decrease in temperature, which is contrary to the property of liquid but resembles that of a gas. The viscosity of helium 2 is practically zero and it can flow rapidly through the narrow capillary tubes. The thermal conductivity of liquid helium 1 is similar to that of a gas at ordinary temperatures, but the thermal conductivity of helium 2 is about 800 times greater than that of copper and silver even at room temperature. See the specific capacity curve. The specific of helium increases gradually if the temperature is increased. At 2.19 Kelvin, the specific decreases rapidly. The liquid helium below 2.19 Kelvin is called helium 2. Above 2.19 Kelvin is called helium 1. The specific heat of liquid helium first decreases and then increases up to 2.19 Kelvin. At this temperature, there is a sudden and abnormal decrease in the specific heat. Decrease. At 2.19 Kelvin, the specific heat suddenly decreases. What are transport properties? According to the kinetic theory of gases, the molecules of a gas are moving constantly in all directions with various speeds. If the gas is not in equilibrium state, we may have the change in viscosity, thermal conductivity, and diffusion. Hence, these phenomena are called transport phenomena. The viscosity, conduction, and diffusion represent the transport of momentum, energy, and mass respectively. In